All right, today we are going to keep on talking about normal probability distributions, specifically by talking about the central limit theorem. So in this section, we're going to learn what the central limit theorem says and how we can apply it to help us out with some really meaningful and important applications. So the central limit theorem says for all samples of the same size n, with n greater than 30, the sampling distribution of the mean can be approximated by a normal distribution with mean mu and standard deviation sigma divided by the square root of n. All right, so let's dig into this. So when we're given a population with any distribution, then it has mean mu and standard deviation sigma. We're taking simple random samples of all of size n from that population. And then what we're doing is we're checking that n, our sample size, is greater than 30. And we know that the mean of all of the values of x bar, so if we take the means of all of our samples, and then we take the mean of the means of the samples, we're going to get the population mean. Similarly, with the standard deviation, if we take the standard deviation of all of the values of x bar, then we're going to get the population standard deviation divided by the square root of n. And because of this, we can convert to z-scores for x bar by using z equals x bar minus mu divided by our standard deviation divided by the square root of n. So times when you shouldn't use this. The original population is not normally distributed and n is less than or equal to 30. So our sample size has to be greater than 30 if our original population is not normally distributed. All right. So when you're trying to solve problems with this considerations, the first thing you're going to do is you're going to check the requirements. So when we're working with the mean from a sample, we need to verify that either it's a normal distribution, like the original population has a normal distribution, or our sample size that we're looking at is greater than 30. So then we also need to know, are we looking at an individual value or a mean from a sample? So if we're dealing with a single value, then we use our z-score conversion that we've used all along, z equals x minus mu divided by sigma, right? But if instead we're dealing with the mean, that sample mean, the x bar, then we need to make sure that we're dividing our standard deviation by the square root of n so that we're using the standard deviation of those means instead. All right, so a little bit of notation stuff. You might have noticed those subscripts with the x bar. All right. So what that means is the mean of all the values of x bar is mu sub x bar. To say the mean of x bar, it's all right. Same deal with the standard deviation. And the standard deviation of those sample means is sometimes called the standard error of the mean and sometimes denoted with the capital SEM deal. So let's look at an example. So if we're trying to safely load elevators, if you read the placards in elevator cars, they usually give a weight and a number of passengers that's safe to use. So one such elevator placard says 4,000 pounds, 27 passengers. So this converts to a mean passenger weight of 148 pounds when the elevator is full. So as far as like average weight, mean weight, goes, so adult males have the highest mean weight. So worst case scenario, we would have 27 adult males on the elevator. So we're going to assume that, and we're going to use the mean of 189 pounds as the population mean for adult males, and the standard deviation of 39 pounds. And we're going to use those things to find the probability that one randomly selected adult male has a weight greater than 148 pounds. And we're going to find the probability that a sample of 27 randomly selected adult males has a mean weight greater than 148 pounds. Lucky for us, the population of adult male weights is normally distributed also. So we'll be taking advantage of that. So here we go. We're using the methods that we had. So we are going to convert for part A. We're dealing with an individual. So we're going to use our z equals x minus the mean divided by the standard deviation to convert to a z-score. So we get a z-score of negative 1.05. So we're looking for the area to the right underneath of that normal curve of negative, or to the right of z equals negative 1.05. So when we do that, we find that the area to the left of z equals negative 1.05 is 0.1469. So to find the area to the right, we'll do 1 minus 0.1469 and get an area of 0.8531. So now we've completed part A. So we'll hold off on interpreting it and we'll do part B. So part B, we're asked about the sample of 27 males, the average weight of them being less than 143 pounds, 48 pounds. Yeah. All right. So again, 27 is less than 30. So that's trouble. We can't use the central limit theorem, except the weight of males is normally distributed, so we can use it. All right, so that's how that works. Check the sample size. If the sample size doesn't work, see if it's normally distributed to begin with, and if it is, like it is here, then we get to use the tools that we've developed with our central limit theorem. So we get our mean of our sample means is going to be equal to the population mean, which is 189. And then the standard deviation of our sample means is going to be the standard deviation of the population divided by the square root of n. So in this case, that'll be 39 divided by the square root of 27, which is about 7.51. So what that means for us is that we want to find the area to the right of 148 as a mean for our sample, right? So when we do that, we're going to use our conversion where we're taking the sample stuff. So we'll have 148 minus the population mean of 189 divided by that standard deviation of the sample means, which is 39 divided by square root of 27. And when we do that, we have a z-score of negative 5.46. If we mark where that is on our graph, it's way to the left. And we're interested in all of the area to the right of that. So if we go to find the cumulative area to the left of z equals negative 5.46, we get 0.0001. So if we take 1 minus 0.0001, we get 0.9999. That's the area to the right of our z-score of negative 5.46. So let's interpret these things. So the first part, in part A, there was a 0.8534 probability that an individual male will weigh more than 148 pounds. And from part B, we've got a 0.999 and so on probability that 27 randomly selected males will have a mean weight of more than 148 pounds. So, given that the safe capacity of the elevator is 4,000 pounds, it's almost certain that it will be overweight if it's filled with 27 randomly selected adult males. Luckily, it's rare that you would ever have 27 adult males decide to all pile into an elevator together. Get a little tight. So, let's take a look at an introduction. We're just going to scratch the surface real quick of hypothesis testing. We've actually scratched the surface this way before, just a little bit, but we didn't do an example. So we're going to do an example here. But again, here's the idea. We have some assumption that we're making. And if we find the probability of a particular observed event is very small, if the events occur significantly less or more than we were expecting, given whatever our assumption was, then we conclude that the assumption's not correct. So, example, body temperatures. So, you all have probably heard the human body temperature normal is 98.6. So, assuming that that is the case, then we have a population standard deviation of 0.62 degrees Fahrenheit. This is based on some data from University of Maryland researchers. And we're going to take a sample size of 106. All right, so 106 people randomly selected. We're going to find the probability of getting a mean of 98.2 degrees Fahrenheit or lower. So we're going to work under the assumption that the population of the human body temperatures has a mean of 98.6. That's the type of assumptions we're going to make. So here's our assumption here. 98.6 is mu. All right, that's our population mean. So we don't know anything about the distribution of the population, but our sample size is 106, which is greater than 30, so we can use the central limit theorem. And we know that the standard deviation of the sample means should be the standard deviation of the population divided by the square root of n. So doing that, we get our standard deviation of our sample means of 0.06021997. So here we have a figure. All right, we draw a graph. We label 98.2 on there, we label 98.6, and we're going to calculate the z-score that corresponds to 98.2. So 98.2 minus 98.6 divided by our standard deviation of our sample means is going to give us a z-score of negative 6.64. So we label that on our drawing, and since we're interested in a body temperature as extreme as 98.2, and 98.2 is below our assumed population mean, then we're interested in getting body temperatures less than or equal to 98.2. So that means we're looking for the area to the left on our graph. All right. So if we look on the chart, negative 6.64 is off the chart, but the value for negative 3.49 is 0.0001. So the cumulative left area of z equals negative 3.49 is 0.001. So ours has got to be that or less. So it's incredibly unlikely. So what this result shows us is that the mean of our body temperatures, if it really is 98.6 like we assumed, then there's an extremely small probability, like really almost impossible, of getting a sample mean of 98.2 or lower. when there's 106 subjects that are randomly selected. So the University of Maryland researchers who gathered the data that they had 106 participants and they got their standard deviation that we used from that, they really did get a mean of 98.2 degrees Fahrenheit. So one of two things had to have happened. Either the population mean really is 98.6 and their sample represents a chance event that is incredibly unlikely, extremely rare. Not impossible, but extremely rare. Or the population mean is actually lower than the assumed value of 98.6 degrees. And so their sample is more typical. Because the probability is so low that we got that sample by chance, it's more reasonable for us to conclude that the population mean is lower than 98.6. So what we're basically saying is, hey, you know what? It's actually kind of likely that our assumption was wrong. All right, so in reality, it appears that our true mean body temperature is closer to 98.2. That might be pushing what this is showing us, but saying that it appears that our true mean body temperature is less than 98.6 is a totally reasonable assumption to pull away from this. Finally, we were talking about replacement being important so we get independent events, and if we've got that 5% rule met, that we don't have to worry about replacement happening or not. So here's a way to deal with no replacing happening and having a sample that's greater than 5% of the population that we're dealing with. So when sampling without replacement, so our events can't be considered independent, and our sample size is greater than 5% of whatever our finite population is. Finite population size is capital N, sample size is lowercase n. We can adjust the standard deviation of sample means by multiplying it by this factor of the square root of capital N minus lowercase n divided by capital N minus 1. Right? So that's our way that we can deal with events not being independent the way we want and our samples being too big to ignore it.